In this tutorial, we are going to discuss light-dependent resistors. Light-dependent resistors are light sensors that can be used in many useful applications that require light sensing. We will look at how we can use light-dependent resistors with an Arduino UNO and LabVIEW Community Edition. So first, let us look at the hardware that we need for this tutorial. First of all, we need an Arduino UNO R3, as usual, some fixed value resistors, a light-dependent resistor or an LDR, a battery or a power source in order to power up our electronic components, a breadboard, and finally some wires and a USB cable to connect our Arduino UNO to our laptop or PC. So what's a light-dependent resistor? A light-dependent resistor, also named LDR, is a special type of resistor that works on the photoconductivity principle, meaning that resistance changes according to the light intensity. So whenever light is being shined on an LDR, its resistance decreases. So its resistance decreases with an increase in the intensity of light and vice versa. It is often used as a light sensor, light meter, automatic street light, and in areas where light sensing is required. An LDR is also known as a photoresistor, a photocell, or photoconductor. So all of these, they mean the same thing, a light sensor or an LDR, light-dependent resistor. So let us compare an LDR to a potentiometer. So in our previous tutorial, we talked about potentiometers. And for potentiometers, they are resistive sensors because we can provide at the input a mechanical action by rotating the knob, for example, for this rotary potentiometer, and at the output, we expect a resistance change. So this is simply a resistive sensor. The input is mechanical and the output is electrical in terms of resistance change. An LDR is also a resistive sensor. In terms of output, it has the same output as a potentiometer. In other words, its resistance or output resistance changes with a change in the input, which is quite different compared to the potentiometer, which is light in this case. So by shining a different amount of light on an LDR, its resistance will change. So the input is optical, depending on the amount of light that we shine on an LDR, compared to a potentiometer where the input is mechanical. So we can see right here two resistive sensors that have the same output change or the same output type, which is resistance change. However, they have different inputs. And of course, we can use these types of sensors depending on our applications as mechanical, mechatronics, or computer engineering students. Perfect. So let us carry on. So how can we measure the output change of an LDR or the resistance change? As we have seen in our previous tutorials, since it's a resistive sensor, which is very similar to a potentiometer, we can simply use a simple voltage divider circuit. So we can see right here our voltage divider circuit, where we have the LDR or the sensor, which is connected between the power source, which is plus 5 volts in this case, which is derived from the Arduino UNO, and the fixed value resistor. And for the fixed value resistor, we need to connect a proper fixed value resistor depending on our application. And we will see how shortly. Now what we can do is measure the voltage output between the connection between our sensor and the fixed value resistor and the ground. And this is simply a voltage divider circuit. If you're not familiar with a voltage divider circuit, please refer to our previous tutorial where we describe it and explain it in great detail. Now, the voltage output right here is simply the fixed value resistor R over the resistance of the sensor plus the resistance of the fixed value resistor times the Vs, where Vs is the voltage supplied and Vout is the output voltage simply across the fixed value resistor. And here you can see the schematic for connecting our LDR to our Arduino UNO. So we can see simply that we have the voltage divider circuit where our LDR is connected to the +5 terminal right here on the Arduino UNO. The other terminal of our fixed value resistor is connected to the ground, and simply the junction connecting our fixed value resistor to the LDR is connected to the first or the analog 0 pin on the Arduino UNO in order to acquire a continuous signal from our LDR, which is, of course, our continuous signal is converted to a digital signal using the analog to digital converter on our Arduino UNO. Perfect. Now the question is, what value of R, or what value of resistance, should we choose for our fixed value resistor? Or what measurement parameters should be taken into consideration whenever we're selecting R? This is a very important question right here that we need to ask ourselves, and we need to know how to design it properly. But before we go ahead and do that, I want to just show you what we have in front of us right here. So first of all, I have a multimeter right here, which is connected to an LDR right here. And we have our LDR circuit that we have just seen, which is connected to the Arduino UNO. Before we get started, what we need to do is just to measure. So let me just activate this one. All right, so it went to sleep mode. So let us activate our multimeter and see what kind of, or what value of resistance are we measuring currently. So as we can see right here, I have my LDR right here, and we can see the current value of resistance is 0.75 to 76 kilo ohms. And this, of course, depends on the amount of light right now that is hitting my LDR. Now, if I try to cover my LDR, I can see that the resistance increases dramatically to 1.5 kilo ohms. So it doubles. And if I let go, where more light is being shined on my LDR, its resistance decreases. I can still decrease it further by shining light from my mobile phone. So as you can see right here, if we shine some light, you can see the resistance is decreasing. And of course, the higher the intensity of light, the less the resistance, as you can see right here. Perfect. So now we can clearly see that depending on the amount of light, the resistance will change across the LDR. Now, instead of using our multimeter right here, what we will use is the Arduino UNO in order to acquire our signal, measure it, use it in useful, for example, control applications, be able to monitor it graphically and numerically. But before we do that, and before we hop to MATLAB, it's important to know how do we choose this resistance value R right there, depending on our condition. So first of all, what we are going to do, we are going to write this equation right here, which is the voltage divider equation, in a slightly different way in order to understand what we need to take into consideration whenever we need to design our LDR, because we need to take two important parameters into consideration, which are sensitivity and range of measurement. So what's sensitivity and what's range of measurement? Let's first of all go over that, and then we will explain them in great detail. So sensitivity means how much does the voltage change for a given resistance change. In other words, it's delta V by delta R, which means graphically it's the slope, as we will see in a second. In other words, it's the slope at a given nominal operation point. The goal for us is to maximize the available range and sensitivity of the measure. However, we have an optimal point between the two. We cannot maximize both at the same time, as we will see in a second, and that's why we need to take into consideration both the sensitivity and the operating range on either side of the measurement. In other words, we need, if, for example, our nominal operating point is at a voltage of 2.5 volts, we need an equal change on either side whenever we shine light or in the absence of light, in order not to have a skewed range on both sides. So let us go ahead and really explain these points in great details. So first of all, let us rewrite right here our equation for our voltage divider. So we know that V out is equal to R over R sensor plus R times V in. Now what we can do right here, we can simply write that V out over V in is simply R over R sensor plus R. And now what we can also do is divide both the numerator by R and the denominator by R. And we will end up with an equation that looks like that. V out over Vs is equal to 1 over 1 plus Rs over R. Perfect. Now what we can do is we can multiply right here by 100 and say that the ratio V out over Vs will give me a percent of the full scale reading. So F of S stands for full scale FSR, full scale reading or full scale deflection. All right, whatever you're familiar with. So what does that mean? Let's rewrite it and fully explain. So V out over V in is equal to 100 over 1 plus Rs over R percent of full scale reading. Graphically, what this means is the following. If we want to plot the ratio right here, V out over V in, which is the percent of full scale reading, which is V out over V in, which ranges between 0 and 100%, versus the ratio here, Rs over R, we get the following trend right here. So let us see at the extreme points, what do we have? First of all, if Rs over R is equal to 0, which means in this case Rs is equal to 0. So we have very, very small resistance for our sensor. What we will get is V out over V in simply. So V out over V in is equal to 100 over 1, which is equal to 100% of the full scale reading. So simply we're right here at the point 100. However, if Rs is very large, much larger than R, so way larger than R, in other words, we can say that Rs tends to infinity, simply V out over Vs will be 100 over infinity, and this simply 0. So what we can see right here, that right here, we will have a hyperbolic-like function, and it's a decaying function. And what we can see right here is that when Rs, the ratio Rs over R is very large, the V out over Vs ratio will go to 0. However, we know that V out over Vs, we still need one more case where Rs is equal to R. When Rs is equal to R, we will have 100 over 1 plus 1, and we will have 50% of the full scale reading. So at a point right here, at 50%, we'll have here at a ratio of 1, we'll have 50% of the full scale read. Now, what do we mean by maximizing sensitivity and maximizing or having roughly an equal range on either side of the nominal operating point? In our case, our nominal operating point, so let's define it here, our nominal operating point will be the resistance in ohms or kilo ohms at a certain light intensity. And usually we measure light in lux or the luminance in lux. All right. So for example, let's say our nominal operating point, okay, in our scenario is, let's say, 300 lux. And for this 300 lux, we know that the resistance of our sensor, Rs, let's say is, for example, 4 kilo ohms. In this case, this is our nominal operating point. So we know that at the nominal operating point, our resistance for 300 lux is 4 kilo ohms. This is the output resistance of our LDR. And the amount of light right here may change above 300 and below 300. And we need equal range on equal side of the measurement of this operating point. Plus, we need to maximize the sensitivity. Now, first of all, what's sensitivity? We said that sensitivity is the slope, which means how much voltage change or how much voltage change will I get for a given resistance change or for a given light intensity change, because light intensity is proportional, of course, to the change in resistance. In other words, it's the slope on this curve right here. So at a given point right here, it is the slope. So I can see that, for example, right here, when Rs over R is less than 1, I have a very high slope or a steep slope. However, at the nominal operating point, I have somehow a medium slope right here. So I can say a medium slope or sensitivity. Here I have high slope or high sensitivity. However, towards the end, when Rs right here over R is much larger than 1, I have very low sensitivity, because simply sensitivity is telling you how much delta V you have for a given delta R right here. And for us to maximize sensitivity, we know that sensitivity is the slope, which means it's delta V over delta R. So in order to maximize it, what we need a large delta V for a given delta R, or for a small change delta R. And I can see right here, for example, if I have small delta V right here for a large delta R, which means large change in the intensity of light, it means the slope here is really flatter compared to a steeper slope right here, where I have large delta V for a small change in delta R. And remember, the change in delta R is in accordance with the change of the light intensity. So we need maximum sensitivity. Of course, I can choose, say, I want this point, and perfect. Now I maximized for sensitivity. But now I need to take into consideration the range. If I look at the range, if you choose R, the fixed value resistor, in which Rs over R is much less than 1, yes, you're maximizing for sensitivity, but what about the operating range? This is our operating range at the nominal point. So in this case, this here is our nominal point, nominal operating point. If I choose for a given Rs at the nominal operating point, R to be larger than it, which means Rs over R is much less than 1. Now on either side of the measurement, look at the range. This is my lower range right here, and this is our upper range. And we can see right here that simply the range is skewed on either side of the measurement. So in other words, if we go into this direction, we have a very limited range. And if we go in the other direction, we have a very large range. And we don't need that. Usually we need what we call an equal range on either side of the measurement. In order to do so, I can see that this is really at the midpoint right here. At the midpoint right here, where Rs is equal to R, I can see that I have roughly an equal upper and lower range or equal range on either side of the nominal operating point, plus I have somehow a medium sensitivity. So this here is our optimal point, where we have medium sensitivity, which is fair enough, and we have equal range on either side of the operating point. So now, how do we choose Rs, for example, in this case? So in this case, how do I choose, the fixed value resistor? We choose it by setting R is equal to 4 kilo ohms, because this is this will set R over Rs over R to 1, which means I will maximize, I will have equal range on either side of the nominal temperature and medium sensitivity, which is acceptable. And this process goes to all voltage divider circuits if I have different types of resistive sensors, such as a thermistor, which is a temperature sensor, an FSR, which is a force resistive sensor, and other types of sensors. So this is very important. So we need to maximize two things. The first one is sensitivity, and the second one is range. Of course, this is not the only way to design it, but this is a very easy and straightforward way to design our fixed value resistor. There are other several ways. So in this case, we'll have medium sensitivity at the midpoint, medium sensitivity, and equal range on either side of the on either side of the nominal operating point. Perfect. So we set RS equals to R. So now that we're familiar with how to choose the fixed value resistor for any given scenario, okay, whether we have a temperature sensor, a light sensor, a potentiometer, or any other sensor, now we are able to construct our circuit and go ahead and program it in LabVIEW. So before we get to LabVIEW, let us go ahead and check once more this slide right here. So we can see right here now that on this graph right here, as we discussed, we have high sensitivity when RS over R is much less than 1. We have very low sensitivity when RS over R is much larger than 1. And we have a medium sensitivity at the midpoint. Now for the range, we can see that when RS over R, we have a skewed range, and the same applies when RS over R is much less than 1. We also have a skewed range. However, at the midpoint right here, what we have is, at the midpoint, is equal range on either side of the nominal operating point. So depending on the nominal operating point, your fixed value resistor will change depending on its value. Perfect. So now we can see, for example, right here, for our nominal operating point, as discussed for 300 lux, if the resistance is 4K, we need to choose a 4K fixed value resistor. So this graph right here, it depicts what we typically have in the data sheet of an LDR. So for each LDR that you get from a certain manufacturer, you need to check its data sheet in order to make sure you fully understand its characteristics in terms of the resistance change versus the light intensity, which is usually measured in lux. So we can see here we have a nonlinear relationship between the light intensity and the resistance. So as the intensity of light increases, we can see that the resistance decreases. And this is what we have seen at the beginning of the tutorial. Now, for this particular LDR, they are telling us that when we have bright light from an artificial light bulb, which is around 1000 lux, the resistance will be around roughly 1K. At 300 lux, it will be 4K. And at 100 lux, which means it's a dark environment, will have a very high resistance, much larger than 4K. At an average light, will have around 4K. So we can see that the darker the environment, the higher the resistance. The more light we have in the environment, or the brighter the light, the lower the resistance of an LDR. Perfect. So from where can you extract such information? From the data sheet of an LDR. So we should always go and check the data sheet of each sensor that we buy, or any sensor that we are using in any application. One more time, we look at the circuit right here for our LDR circuit. So please go ahead and assemble it, and this is it in front of you. So for our case right here, we have chosen a 4.5 kilo ohm resistor, fixed value resistor, and this can be deduced from its color code. And the main reason I have chosen this fixed value resistor, because at my nominal operating point, which is 300 lux, I've got, using my multimeter, 4.5 kilo ohms in terms of resistance. So this is why I have chosen this value. as we have illustrated earlier. Perfect. So now what we are going to do, we are going to go ahead and build this nice interface using LabVIEW in order to measure the resistors. So let us go to LabVIEW and get started with it. Perfect. So first of all, I'm going to create a new VI, or in other words, let me open an existing VI that I have created, an empty VI. And let's place our block diagram on one side and our front panel on the other side. But first, let us build our block diagram. So the first thing we are going to do is to have a while loop, then go to Hobbyist and choose our blocks. So we need to open the connection, close it, and for reading a voltage, what we need is to go to the analog library and choose analog read. Then what I like to do is to align all these and connect them right here. Perfect. So now what I need to do is to here specify the visa. And for me right here, it is COM3. Perfect. Now what we need to do next is just to add right here. Go to dialog, add a general error handler in case we have an error. And then I'm going to my front panel, go to NXG and choose a nice flat stop button. So you can choose any interface you like. I usually like to go with NXG. Then in case I have an error, I want to stop my code either from my stop button as usual or either from my stop button, or in case we have an error, we need our code to stop automatically. Perfect. So now we need to specify what's the analog channel. For us, it's analog channel 0 because as you can see right here, we connected our voltage divider output to the analog input or analog pin 0 right here on the Arduino. So we need to specify 0. And for the output right here, I have the voltage output and the analog input reference, which is 5 volts in this case. And we have the voltage output. So I'm going to go right ahead right here and say create indicator. And for us, it will create an indicator that shows us the output voltage. So VS or V out. And let us go ahead and see if this will work. So what we have right here is our circuit. So let us go ahead and see our circuit in action. And what we have right here on this side is our LabVIEW code. And let's run it. So we can see that the voltage now is 3.6. As I put my finger on the LDR, I can see a right here, I can see a drastic change in the voltage. So the voltage decreases as the amount of light decreases, and it increases with an increasing amount of light. Now what we need to do right here is we need to make our code more efficient. So we should always add right here a slow down a little bit the while loop in order to not overwhelm our CPU. So I will choose a 10 milliseconds right here for the time between two consecutive iterations for the while loop. Perfect. So now what we are going to do next, we are going to go back to our code right here, and we can see right here that now I'm measuring V out. But what about if I am interested in measuring RS directly, knowing what's the resistance in kilo ohm for my sensor? I simply can use the voltage divider equation and right here extract RS in terms of the other parameters, which are R, VS, and V out. And we can see right here that we have VS over V out minus 1 into R. So let us go ahead and implement that in our code. So first of all, I need to divide. So we'll get the divide operator right here, and we need to divide our VS, which is 5. So let us double check it. So we have VS over V out. So VS over V out. So this is our V out, and we need to create a constant right here of 5. So 5 minus 1. So I can simply use the decrement right here, minus 1 times R. So I need to multiply it right here by R. So I need to multiply everything by R. And what's the value of R? in my case, I will choose it as a constant. You can choose a controller right here if you want to change it on demand. But for me, I know that it's 4.5K. And simply what I'm going to do, I am going to connect it right here and say I have RS. So in order to create another controller like that, you just click Control and hold it, and then click and drag, and you will create a duplicate of that. Perfect. So now I have RS right here. So I have RS, and let's see how RS changes by running our code again. So let's run it right here. So I can see right here that the resistance now is roughly 1.7 kilo ohms. As I put my finger, it increases to 8 kilo ohms. As I remove it, it goes back to 1.6. If I shine light using my phone, I can see it goes to 1 point below 1.67. So that's awesome. Now I can stop my code, and what we can do is we can graphically show our resistance change. So let's show it graphically. So what we can do right here is we can simply go to NXG, graphs, and choose the graph palette right here. And I am going to say here output signal, name it output signal. I am going to put on the y-axis the RS in ohms, and we should also here put the unit all in kilo ohms, and here it's not in ohms but rather in kilo ohms. Be accurate, so we should put kilo ohms, and right here that's not the time, that's the index of the loop. Okay, and right here, because this is a waveform chart, so we have the resistance versus the index of the loop, and that's not the actual time, and we will see in a bit how I can plot the resistance versus the actual time. So here I will call it RS versus index, and I will make the line style a little bit thicker. Perfect. And now what we can do, we can go ahead, use it as an icon, align it right here, and we can run our code, and we can see right here that whenever we approach it, the resistance increases, or whenever we decrease the light intensity, and vice versa. So we can see right here that our LDR is working perfectly. So let us see it on the video right here. So as you can see, as I try to cover it, the resistance decreases, and when more light is hitting the LDR, its resistance decreases. Now, one more thing we need to do right here is how can we really plot and save right here the resistance versus time. Right here we have the index, which means this index right here, if I create an indicator right here, we can see right here, if I run my code, this is the index of my loop, and simply it's plotting the index of my loop, the resistance value for each iteration versus the resistance versus the index. But what we need actually in an actual measurement is resistance versus time. So how can we do that? Let's go ahead and try it. First of all, and see how. First of all, what we need is not a waveform chart. What we need is what we call a graph. So if I go here to the classic or the modern palette, I can see here I have waveform chart, which will plot y values against the index. I have waveform graph, and I have xy graph. So in the NXG right here, what we need to choose is the xy graph in order to plot one quantity on the x-axis, which is the time, and another one on the y-axis. So I will again call this one RS in kilo ohms, and I will call right now here the time, and for us it will be in millisecond, and we will know why in a second. Here I will call it the output signal in time. So let's put here time, output signal. Okay, just all right. And here we'll say RS versus time. And we can make the line style also a little bit thicker. And we can change the color right here, for example, to this red. And then we can align these two. We can, if you want to make, if they are, now they are equal in size, you can make them equal in size. Perfect. Now what we need to do, if I try to connect the output signal to this one, of course, an error will occur. Why? Because I've connected two different data types. The data type of the source is different than the data type of the sink. So the sink requires two arrays, one for the y-axis and one for the x-axis, which is the time array. And how can we do that? It's very simple. What we need to do is to simply create two arrays, one for the time and one array to store the values of the output signal or of the resistance change. So to do that, what we do is we go to array, we choose build array, and then we go for two elements right here. And then what we need to do is to store each time in the array. So we need to take the element right here and then wire our array to the while loop and go to tunnel mode and say right here replace with shift register. Now we will have a shift register. So what we're doing right here, we're taking the value, creating an array, and then taking the array with the previously stored values and then increasing the size of the array. In other words, we're creating an array in order to store the elements for each iteration of the while loop. And then we should always initialize our shift register in order to start from scratch whenever we rerun our while loop. Now what we are going to do, we are going to go to create another array, and this time for our time vector or time array. So for that, what we need to do is to go to timing, choose the tick count, which will return the tick count in millisecond or the time in millisecond. However, I need to start from 0. I need to have a 0 reference. For that, we can place one tick count inside and one outside. And before we start timing, what we need to do is to subtract the timing right here before we enter the while loop. Okay, so we need to subtract it. We need to subtract the time before we enter the while loop. We need to subtract the current time from the time before we enter the while loop. Why? In order to start from 0, to have a 0 reference. You can omit that and later on deal with your data manually. However, you can do it right here in LabVIEW. Now what we need to do is to create another array. So let's put this one outside for a second. So we need to build another array right here. And I can take this element right here, tunnel it right here and say replace with shift register, and then we'll put the shift register right here. So let me just decrease it a little bit and then add it to the array. And now I've created successfully two arrays, one for the time and one for the actual resistance values. Now what I need to do is to add these two, one for the x-axis. So for that we go to cluster and we choose the bundle by, not the bundle, but we choose the right here bundle, and then we'll have one for the y, so it will be the second array, and one for the time, which is on the x-axis. So the first one will go to the x-axis, the second array will go to the y-axis, and now I can wire it to my output signal. And now I have successfully plotted the time here for the tick count is in milliseconds. So if I press Ctrl H in order to know what does this tick count, what does it do, I can see that it returns the time in milliseconds value. So it returns the value of the millisecond timer. And I can go to detailed help if you need detailed help. Now if we go ahead and run our code, so let's look at it. And let's put our LDR right here on this side. So we can see right here now that it's saving the data versus the value. Now, if I go ahead and run my code again, I can see that there's something missing, which is to initialize our shift register. And let's run it again. Perfect. And as you can see now, I am recording my data versus time. Now we can do something else. If you don't want to use the tick count, of course, the tick count is more accurate. What you can use is the elapsed time. So you can go to timing, choose the elapsed time right here, okay? And we'll just show you a similar fashion. So I will delete this one right here. I will say elapsed time, and I will create another array with the elapsed time just to show you another method. Let me delete this one and create a constant right here. And now, if I go right ahead and run my code, I can see that it will record the elapsed time versus, or the resistance change versus the elapsed time. And all what I need to do right now is to stop my code. And if you need these values, of course, you can export them and use the measure or use the measurement save to measurement file, VI, which we will discuss in future tutorials. So you can export your data to the clipboard or to Excel, and you can change right here the significant digits for the X and Y axis in order to get the desired significant digits. And that's pretty much it. So let's run it one more time in order to make sure everything is working fine. So it's working fine. Our resistance is changing. And this is it for LDRs or light dependent resistors.